Okay, let's try question it. David carries out an experiment to investigate variation of magnetic field with distance, and it's a single current carrying wire, so that's fine. We're measuring distance as A, so that's convenient because the formula for this is I mu naught over 2 pi A, isn't it? That the letter A is used. Varies the distance, measures the flux density, current is kept constant, that's good to know, and results in the table. Okay, so we're given the equation, happy days, and it's rearranged it for us. I think arguably we could have managed that algebra, but it has rearranged this for us. Use this data point to calculate a value for the current, so no problem here. Yeah, not sure why it's done the rearranging for us. To be a little bit careful with units. 10 centimeters, 0.1 meters. We don't want to use centimeters. And similarly here, look, the flux densities are given in millitesla. So this is the data point we're using. Times 10 to the minus 3 millitesla. That's all over mu naught. Mu naught from the formula sheet is 4 pi times 10 to the minus 7, and that's henries per meter. So we can actually cancel the pi's out of this. So we can get slightly less for me to type into the calculator. So chuck that in the calculator, bear with me. 0.0195 times 10 to the minus 3. 9.75. That is quite a lot of current. 9.75 amps. I'm just going to check my calculations again here. Let me do that in the calculator again. I don't use a very good calculator, people, and I am actually quite prone to horrific calculator errors. I really should use a proper calculator, but I don't. I use a rubbish calculator. Anyway, 9.75 I've got a second time, so yeah, that seems fair enough. To be fair, in an experiment like this, you would need quite a large current to get anything measurable, but 9.75 amps will melt most thin copper wires, won't it? Anyway, yeah, 9.75. Okay, I did have a sneaking suspicion we were going to have to draw a graph here. Draw a single line of best fit in bold. Look, single line of best fit. Yeah, there's no uncertainties here, I suppose, no repeats, so it is just going to be a normal line of best fit. Standard rules for a line of best fit, you want roughly the same number of points above the line as below the line. Obviously, the gradient of the line should, as best possible, represent the data that you're drawing a line of best fit for. So in general, no requirement to extend your line of best fit beyond the data that you're given. So unless the question actually asks you to do that, I would generally suggest don't. So something like that is going to be my line of best fit. It's a single mark here, so as long as it looks pretty appropriate and you don't have all of the points on one side of your line of best fit, you're going to be okay, I would have thought. Use the graph to determine the distance from the edge of the phone to the center of the hole probe. See diagram. What? Use the graph to determine the distance from the edge of the phone to the center of the hole probe. Oh, I see. Okay, so the hole probe is somewhere inside the phone, but A is being measured to the edge of the phone. So there will be some extra distance, X, to that hole probe. We're plotting here 1 over B. We're not plotting B. Oh, that would have been a strange result to get, wouldn't it, if we were. So if we think about this, our equation is this one. B equals mu naught I over 2 pi a, but we're plotting 1 over b against a. So a rearrange of that, 1 over b would be equal to 2 pi over mu naught I times a. So that should pass through the origin. However, the fact that we've got this little bit of extra distance means that it won't. So what we'll do is extend our line. We're going to extend our line of best fit like that, somewhere like that. This intercept, this is our offset. The effect of that offset, if you think about what that does to our measured distance, it basically shifts everything, doesn't it? So that offset, if we took that away, our entire line would shift to the right. All of these numbers aren't quite right. They should all of our points should be moved across by whatever that offset x is, and that would just move our line across. So this intercept is going to tell us what's going on here. So that is 2 minor grid lines. Each of these minor grid lines is 0.2. So 0.4 centimeters. I'm just going to put in brackets x-intercept. Okay, hopefully that makes sense. After me telling you not to continue your line of best fit, but I did say unless the question tells you to, and this hasn't told you to specifically, but that's what we need to do. Determine current in the wire. So yeah, so if we look at this equation that we had before, 1 over b is equal to 2 pi over mu naught I times a. Therefore, the gradient of our graph equals 2 pi over mu naught I. Therefore, I must be equal to 2 pi over mu naught times gradient. So anytime you're finding a gradient from a graph, always just make it really clear on the graph which data points you've used. Just it's so much easier to mark. So I'm going to and also use a nice big triangle. Don't use some like tiny. You've got a lot of data to choose from. You've got an entire graph page, so use it. So that comes down to there. I don't think I've crossed from one line to another. That is 12.2. Crosses here at minus 0.4. And similarly, that is, what are these? These are just units. Those are just one. And I would go ahead and label on it delta 1 over b is equal to 62. Careful with units, always. And that's Tesla's -1. Okay. It's not so much the units here that we need to be careful with. It's the 10 to the 3 that we need to be careful with. And then delta a is equal to 12.2 plus 0.4, 12.6 centimeters. So gradient y over x, 62 times 10 to the 3 divided by 12.6 times 10 to the minus 2, 0.126, whatever that is. (4.92 times 10 to the 5). And then we're just going to sub that in. So I is equal to 2 pi mu naught 4 pi times 10 to the minus 7 from the formula book. So pi's are going to cancel. Times our gradient, 4.92 times 10 to the 5 equals whatever. Uh, 10.2 amps. And that's not a million miles from the previous number we had, so that seems okay. Final part then. David measured the current in the wire as 10.5 plus or minus 0.5. Okay, that is legit. Evaluate the quality of the data obtained in this experiment. 4 marks. 4. Okay, well, I guess first things first, 10.2 is within uncertainty for current. So that's okay. Typically when it says evaluate, you have to do some sort of calculation. And I'm not really seeing what that would be, given that we don't have uncertainties here. We don't have repeats. We don't have anything like that. Evaluate the quality of the data. We expected a straight line, and we have got a straight line. So yeah, I guess, yeah, I think what I'll do, because I feel like the presence of the word evaluate is making me think I've got to do a calculation. And honestly, 4 marks, I'm struggling with what I need to do for 4. 0.5 over 10.5. What is that as a percentage? That is 4.76%. Uncertainty in current. But the problem is we don't know the uncertainty for the distance measurements, so that's not particularly meaningful. The points in my graph are close to a straight line, so that is worth mentioning. So we have got a straight line and all of the points lie very close to it. Data is in a straight line. I mean, I've done this calculation. Are all of my points within 4.76% of the line? You know, for 4 marks, you're not checking every single data point, are you? That's not happening. I mean, they look like they are. Data is in a straight line with all points close to line. Okay, I am struggling to see what else to do here. We would expect a straight line, and we've got one. All of the points are close to the line. I don't know. Maybe. I mean, I'm just wondering about this 0.4 centimeters. If we go back to this data point, put the 0.4 in, so that instead of 10 centimeters, it's 10.4. Does that give us a current that matches? That seems like, I don't know. I just don't know really what it's after, to be honest. You know, normally if there's a graph and you're evaluating quality, you're talking about maybe the size of error bars or the range, but there's no uncertainty given really. We've got a single line of best fit. So all I can really say about that is that the data is close to that straight line. I don't really know what else to put. I find it hard to believe that we would have to adjust all of the calculations with the 0.4 centimeters there to check that current is within uncertainty. That seems unlikely. Yeah, so I think I just stop there. Not entirely sure. I'll check the mark scheme for that one. I want to finish the paper without looking at the mark scheme though, so I will at some point maybe come back and talk to you about what the mark scheme says for that. I'm not really sure what they're looking for 4 marks there. But obviously in terms of exam technique, there's no point. I should definitely be moving on to the next question. It's not, I've already spent more than 4 minutes thinking about it. Anyway, that's it.